Oh, wow.
Yeah.
Wow. Wow.
Yeah, but he was telling me that.
So tough.
Yeah.
Hi guys, can you hear me?
Hi, Victor.
Yes.
Yes.
Yes,
Yep.
we can.
Okay. So how was the TA section?
Good.
So I also uploaded the problem set solutions now.
Yeah. Number 3 was confusing. Number 3, 3B, right? 3B was the one, you know.
Yeah.
Yeah, we can go over that at the end of the class.
And
Oh.
even for 3C, I was
Even with 3C as well.
I had the right idea, but I changed it to something that was wrong. I was overthinking it.
Yeah, so
I used a vector value function.
we can go over it later at the end of the class. There was a problem, an exam question I did at some point.
Was a problem 3, Victor, was problem 3B from like a paper, like a, is there something like a Richter function, something I was checking, like Richter, Felig, some sort of utility, something like that? I was reading something as a journal paper.
Yeah, so
Same.
Rick, I forgot the name.
Yeah, but this is, yeah, so sometimes there are some things that are on papers, but this is kind of a simplified version, right? The paper version will be way more difficult.
And Victor, I believe you mentioned this before, but you said you were changing the material for this this time around?
Yeah, so thanks to GitHub, you can check the changes I made, right? For this class, I already did the changes Monday, Tuesday. So this was the proof of the Afriat theorem, and I revised it, and I moved also material. Previously I was proving the strong axiom, the thing, so the strict version. Now I'm proving the guard version. So this proof is just cleaner, and yeah. So, but you can check. So this time around, I didn't change anything because I read it Tuesday, so we were unable to cover all the changes I did anyway. So I also added some paragraph with this measurement error stuff. And then for next week, I'm gonna get basically a new chapter with a stochastic choice. If we finish today, depends, it's kind of long. Okay. So let me, okay guys, so right now we're gonna start with class. Let me share screen. So everyone can see my leaks file?
Yes.
Okay. Okay, so just a reminder. So right now, we finished the theory of the utility maximization problem. And so we were left with the task of trying to test this data in an experimental data set or some data coming from service, from scanner data, okay? So in particular, I'm interested in testing whether a collection of prices and consumption bundles, a finite collection, can be compatible with rationality or not. So again, so where this data comes from. So one example is the experiment I told you. So this is the data set, right? This calligraphic O. So now examples of real life data sets are the ones that I told you in the experiment. So this is an agent that is faced with graphical representations of the budget line. So the vector is a vector of size 2, right? And then you pick a point in the budget line, that's the X. So X1 is gonna be the first trial, X2 is the second trial until X50. So here we have P1 until P50. And the income, because you have to live in the budget line, is just the multiplication of price times X. So in this case, for this experiment that I show you, income is always fixed to 1 token. Okay, so token is this currency you use in experiments. So what experimenters do is they create exchange rate between tokens and dollars, so to enable to actually give you then a meaningful payment. And then the way they do is they actually pay. Not every trial you do is gonna have a compensation. Rather, you're gonna pick one of the 50 at random, uniformly at random, and consumers are told about that. And then you're gonna be paid according to that particular choice. So in this choice under uncertainty, the experimenter is gonna flip a coin, the state of the world is realized, and then you're gonna be paid according to the portfolio that you chose. Okay, so that's one example of a real life data set people have collected. Another example that is typical is survey data. So this is the typical data set of households and consumption, right? So one of the famous ones is in Spain, is the survey of budgeting allocation, so encuesta de presupuestos. So that one is very famous because it's one of the few that are completely open, and is also a panel data set. Okay, so you can actually go to the Spain Statistical Agency and download it. So a lot of people use it. This data set, what it collects is what consumers remember consuming the last every quarter. That's the frequency. I think they change it. No, it's always a quarter. So they keep a diary of different consumptions of different goods, and then they record this information. So they follow the same household across quarters, and then basically this survey then produces just the consumption bundle at each period of time and each location. So there is no prices in that survey. So how do we add prices to that survey? So the statistical agency in Spain also collects these price surveys. So price surveys, they send pretty much their employees, the statistical agents, to check what are the prices in shelves, so the stores around a particular city. So usually you have to pick a geographic division. So in Spain, I think they have I don't remember exactly, but they have the main cities, right? And then they have kind of regions. So it's never fully granular, so you have to do these big divisions. And again, usually you have Madrid, Barcelona is going to be there, but you're going to have the rest are going to be big regions. And using that, statistical agencies are going to report not the granular price of, say a bag of rice, a kilo of rice. No, rather they are going to aggregate this into composite goods called, for instance, food, transportation, recreation, clothing, and then they're going to create a price index, right? This consumer price index, the CPI. Okay. And then what you do to create a data set that you can test these theories on is going to be to aggregate the consumption of household that is actually at the level of the good to these categories like food, recreation, transportation, and so on. And then in order to match this data with the price data from the statistical agencies at the regional level and at the time level, okay? So the match is in terms of location times time. That defines a market, and basically they are facing this price index. So for surveys, you notice that this is not really it's not really a utility maximization in the sense of actually choosing goods, but rather is a budget allocation problem, right? Because you are choosing, the household is choosing how much money out of the total expenditure in a month, what fraction of that expenditure is allocated to each category, right? So this is still a utility maximization problem where you're actually choosing what fraction of the total expenditure is spent on food versus recreation versus clothing versus transportation, right? So this problem still can be described as a utility maximization problem. So this is the second way people test. And whenever you see test of rationality or GARP in survey data, is going to be this aggregated across goods data. So actually categories of goods, okay? And prices here are going to be CPI prices, consumer price indexes, okay? And then commodities are going to be composite commodities, so categories of goods. The third kind of data that we use is the scanner data. So what is the scanner data? So one of the most famous ones is the Nielsen scanner data. Nielsen scanner data, basically Nielsen, this consultancy firm, they pay people in order for them to actually scan the products they buy when they go to a supermarket. So some of you, actually in Canada, you can actually form part of this. So it's a way to earn money when you're in grad school, right? So you go to this Nielsen thing and you register yourself as a member of the panel. And then each time you go to the supermarket and you come with your groceries, you're given a scanner, right? And you can scan the barcode of the things you purchase. And then basically that means that you're gonna get a software, an app, is gonna tell Nielsen what quantity of bags of rice, loaves of bread, produce, kilos of meat, whatever you buy, each trip, right? So the unit of observation there is a trip, so it's a time period. So then, because you scan the barcode, you're actually giving them already the description of the product. However, you have to input using their app, you have to put numbers for the price. So you actually say, this cost me such and such, right? So you put the prices on. And if you have coupons, you also have to say, I actually use a coupon, so and so. So this data actually is really good at capturing quantities, right? And then prices are also reported themselves. So you don't use CPIs, you actually use prices inside the data. So the only issue with that data is that you only see prices for things that were picked by the consumer, right? So if someone didn't pick an item, so you never purchase cereals, you don't like cereal, right? Then I'm never gonna see the price of cereal you were faced. So to solve this, Nielsen did actually another data set, which is a wholesaler data set where stores like Costco, Walmart, and others report the weekly average prices of goods in shelves, okay? And then at the barcode level. So that data, of course, is more modern, and that's where now people are using to test functionality. But in the end, you're going to get consumption bundles, right? And then you're going to get also. Okay, so you're having issues now with echo. Okay, let me see what's going on. So is everyone with mute? Yeah, thanks. Yeah, so that was the issue. So let's go back. So whenever someone is not mute, it creates the feedback, right? No. So this, the third data set, the scanner data set, is of course granular and has prices at a very granular level. So there's actually one of the new sources to test functionality, and actually it has real prices, not as opposed to service, which is CPI, Consumer Price Index. Okay, so experiments, of course, are the gold standard as usual. So right now, I want you to focus on the experiment, and that's the kind of data.
Sorry, I think there's still some noise going on in the speech. It's very.
It's not as much as an echo. It's
a noise.
recortado.
I think it's my computer. So is the noise now better?
It goes away sometime, and it just kind of shows up and it stays for a little while.
I think it's so. I'm having some issues with my internet connection. It seems that it's Rogers, so it might be just noise because of that. So this is the ping noise. Okay, so now it's better or not?
It's good now, yes.
Yeah. Okay, so if it's not working, I'm gonna try to use another. Yeah, I'm gonna try to use another microphone I have. But yeah, let me try that. Quickly. So this, I think mainly is an issue with the internet, but the noise sometimes can get reduced with this stuff. So, okay. Okay. So I hope it's now more bearable. Okay. So we want to define, again, these definitions of revealed preference, as I told you last class. The one I want you to remind you is the GARB, right? So GARB is telling you that this is a condition, of course covers a warp as a special case, but this one tells you that if you have a chain of revelation, x1 to x2, x2 to x3, and so on until xn, then, it cannot be that xn is the strictly root referred to the x1. Or in other words, if you have in fact a cycle, then this cycle must be weak in the sense that everyone has to be in an indifference, right? So in that sense, we are allowing only cycles of indifferences, or else there is no strong cycle, right? That's GARP. Of course, with this in hand, we're going to show that this, as I told you, the Afriat theorem tells you a cool equivalence between 4 statements. So that means the first one is that if you can actually rationalize a data set in the sense that you can find a utility function that such that the observed xk is actually at the top, is the best item in the budget set, even by PK menu with this income. So here, of course, there is a small typo here. It should be K. And the budget, of course, is PK times XK. And then I'm telling you that this is the top in the budget. And the key property of this utility is just that it's locally non-satiated. I don't need anything else. I don't need continuity. I don't need concavity. I don't need anything, right? This, of course, implies GARP. GARP then implies these inequalities that are called the Afriat inequalities. The meaning of these inequalities basically are computational. So you can use them to test rationality in an easy way. And then finally, you also have the equivalence with the existence of a continuous, concave, a strictly monotonic utility function that rationalizes the same data. So Afriat's theorem is telling you something very powerful. It's telling you, look, we actually have the same utility can generate, sorry, the same data set can be generated by 2 utility functions. One that may be very weird, right, with a lot of kinks, maybe non-concavities, even non-continuous with jumps, and another that is continuous, strictly monotone, and also concave. So for finite data, you can always use a nice utility function, right? So in particular, convexity of preferences here is not testable, right? So any finite data set can be rationalized by a convex preference relation. Okay, so the first thing I want you to notice is what we're doing. So here we're doing actually something is almost magical, and I want you to realize the importance of this term. So initially, as we discussed in the previous classes, is that people thought that testing rationality was super hard, right? Why? Because basically you say utility is an observed, okay? Utility is a function, so you don't observe a function. Now, utility maximization is the hypothesis that there is one function, right, defined over all the choice set, such that if I maximize it, then I generate the data. Now, so what will be the econometrician's approach to it, right? So the econometrician's approach to it will be a brute force approach, right? You will parameterize the utility. You will, for instance, propose a utility that is potentially Cobb-Douglas, right? And then Cobb-Douglas has some parameters. You will do some more or less to try to fit to the data. And then, you know, if you don't fit exactly the data, then you actually are rejecting the data, right? Maybe you can do a statistical test and say, you know, given sampling variation is actually also rejected. But then I will tell you, look, what you did is only rejecting Cobb-Douglas utility, not general utility maximization, right? Because you're actually picking a particular parametric family, not the general model. So then you will tell me, then, you know, if you're an econometrician, traditional one, you will say, okay, but that means actually utility is not testable because I will never get the actual utility, right? You see? Because then you will have to have a super flexible polynomial for the utility and so on, right? So what would you do then if you have such a problem? So you have to approximate a function. So now you say, oh, so I'm going to use machine learning, right? So some very flexible thing, and then trying to see if this maximizes the object. But that's actually high dimensional. And as I told you, the problem is NP, so it's actually very problematic to do that. So Afriat is telling us, look, you actually don't have to do anything else than just a linear program, okay? And in finite data, you don't need even to compute a demand. So you just need to check guard, okay? And also equivalently, you can only check first order conditions. And let's do that. The first, we're gonna prove now that if you have for the existence of a continuous concave strictly monotonic utility function, then this implies the existence of these inequalities, okay? As a motivation, pretty much. So if U is concave, a concave function, then by definition of concavity, I have that, assume also differentiability for now, that this following inequality holds. So if you go to a math book and check the properties of concave functions, you're gonna have the following property, is that if I take 2 points in the domain of this function, so xt and xs, here these 2 points are data set, right? Data points in the data set. The utility of xt is less than equal than the utility of xs plus this is the gradient. So this is the vectors of partial derivatives of u, okay, with respect to each good evaluated at xs. And then this is multiplied by the difference of the vectors, xt minus xs. And this, of course, is the inner product. So this, remember, this is a definition almost of concavity. So if you are concave, your function u is concave, then you have to satisfy these inequalities, okay? Now, assume u is smooth, differentiable, and now I compute first order conditions, right? So remember the Karush-Kontaker KKT first order conditions, right? So what did they tell me from the UMP? The UMP told me that the gradient of the u, right, evaluated at the optimized xs is less than equal lambda s, some multiplier, Lagrange multiplier, times ps. So then I just replace this inequality in the inequality above. So you know, because the inequalities are in the same direction, I can do that. And now I obtain this inequality now, okay? Which is exactly looking like this inequality of the Afriat inequality. So what is cool about this is that this is telling you, look, if you have a utility maximization problem and finite points, then you can actually test, of course, first order conditions in the sense that you can look for the numbers of the utility. So now instead of looking for functions, I'm just looking for numbers associated with each bundle. So UTs. UTs are finite because these are indexed by the number of observations you have. So in our experiment, there are 50 UT. And Lagrange multipliers, which happens to be positive. And also these lambdas, how many of them do I have? I also have 50, right? So instead of looking for a function, I just have to look for these 100 parameters, such that they satisfy these inequalities for the data. Now, is this problem hard? No. Notice that this set of linear inequalities is linear. So it's actually linear on the unknowns. So price is observed, x is observed. So therefore it's linear in lambda u, is linear, okay? So you know that solving a system of linear inequalities is super simple, right? It's a very simple problem. So you can actually put it on MATLAB and Julia, and then it will be solved in microseconds, right? So now, you know, I don't have to do machine learning. I don't have to do any weird metrics, any weird polynomial. I actually can check exactly rationality by means of these inequalities. So that's pretty cool, and also very obvious using concavity. What is not obvious of the Afriat's theorem is that by checking these inequalities, I am completely sure that if you pass the inequalities, you can ensure the construction of a utility function, okay? Because everyone can get testable conditions, right? The magic here is that these conditions are not only testable conditions, but are testable and exhaustive. So they are necessary and sufficient. The moment you pass these inequalities, you actually can construct a utility function. So this is also covering the integrability problem. So from points of consumption, I can go back and construct a utility. So now I can talk about welfare, you see? So this is telling me you can do welfare now, okay? And also, you know, on top of that, these Afriat inequalities also telling you that you can actually move, as I told you, from concavity to non-concavity without loss, okay? okay? So it's a very convenient, very powerful theorem. It's mainly about being able to test rationality, okay, and test all possible implications. So the moment you have conditions that are necessary and sufficient, you are testing all the implications possible. There is no more implications, right? So if you pass them, you can actually constructively build a utility. Got it? Okay. So now let's prove it, right? Now that you realize the importance of it, I now want to prove it. Yeah, go.
I just have one question. So Afriat's theorem there, so you have the 4 points, 4 conditions. So are each of these equivalent to each other?
Yep.
Okay.
So the if and only if means that 1 implies 2, 2 implies 1. So basically you can think also of the circle. That's how I'm going to prove it. 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 1, right? But that also implies that the arrows here are actually, the implication, you can define a relation, right? So this relation also happens to be transitive and so on. So you can actually then go also and say 1 implies 2, 2 implies 1, right? So it's an equivalence relation among them. So this is the if and only if relation. So yeah, you can go back and forth any 2 points here. Okay. Any other question? Okay, so now the proof is basically a classical proof. And I'm gonna do this. 1 implies 2. So locally non-associated utilities implies GARP. Then I'm gonna prove that GARP implies the Afriat inequalities, right? 3. Then I'm gonna prove that 3 implies the existence of a concave utility. So I'm gonna build a utility, okay? This is the kind of interesting step. And then finally, I'm gonna prove that 4 implies 1, which is trivial, right? 4 implies 1, it just means that if you have a utility that is concave, locally monotone, right? And or continuous, it's obviously, so it's strictly monotone, basically. It implies locally non-associated, right? So the final one is the simple one. The interesting ones are these others. So let's prove it. So 1 implies 2. What is 1? There is a locally non-associated utility, and your data set satisfies GARP. Okay. So assume the data set is rationalized by a utility function that is locally non-associated, and that GARP fails, so it's approved by contradiction. Then you have that you have a chain. You have a cycle that is strict in the last part, right? So x1 is real preferred to xn, and now xn is strictly real preferred to and directly real preferred to x1. Now that means that I have a chain of utilities, right? By assumption. So u of x1 is greater than or equal to u of x2 dot 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 u of xn. Now I also have, by the last part of the statement, that Pn times xn is strictly greater than Pn x1, okay? But this means, right, that by local association, this is the cool part. So there exists a y close enough for some epsilon to x1, okay? And in fact, you know, this one has to be better because of the locally non-associated assumption. So it has to be that according to the u of y is strictly better than u of x1. But because it's so close, this one is going to be still in the budget of Bpn Pn times xn. So it's going to be inside the budget. So that means basically that that this one is still affordable. Okay. So the only way, you know, these inequalities can hold here is if all these inequalities become equalities, right? Therefore, I'm only ruling out the equality, right? So they cannot be equalities because that would mean that u of x1 is equal to u of xn, and now there exists a y that is better than u of xn, strictly, and affordable. So therefore, u of xn cannot be a maximum, right? So contradiction. Then I'm done. So now I've proven using local non-association that GARP has to hold by contradiction. Okay. Now, 2 is GARP, 3 is Afriat inequalities. So here you have to notice something. So as a motivation, I show that concavity implies Afriat inequalities, right? And so according to the motivation that I did, if you have concavity, the Afriat numbers are interpreted as utility numbers, and the lambdas in the Afriat inequalities are Lagrangian multipliers, right? So the marginal utility of income. However, this proof I'm going to do now is actually not doing that, right? So following the logic is going to just come from GARP and then show that there is these numbers. So this proof is actually very mathematical. The interpretation actually is something called cyclical monotonicity. It has to do with network theory, so it's very deep. But we're not going to go into very existential proofs in the sense that we're going to use some deep theorem. We're just going to construct the numbers from GARP. So I'm going to do a constructive proof. So this is the proof that is the easiest and more accessible for you. But remember that basically this is a consequence of some deep theorems in network theory, in combinatorial theory, and then you can also prove it another way. But in this particular way, it's just a constructive proof, which is the simplest one. So the way I'm going to do it is by using an algorithm, okay? So I'm going to fit the input. So let me change the notation to be on the same line as the statement. So my input is going to be the data set. It's a finite data set and it satisfies GARP, okay? And then the output is going to be numbers, ut, lambda t, are all positive, such that they satisfy the Afriat inequalities, okay? I'm going to have one parameter, which is the number of observations. I'm going to set it to n. Why I'm changing notation here is that the original proof is invariant. So in lemma 3 in variant 82, a paper in econometrics, so I'm trying to use the same notation as he is using. So if you ever have to check the proof and whatever, you have the same notation. So remember, right now, just for simplicity, we're going to set the number of goods to the number of observations of trials in the experiment to n. Okay? And so now, this, I'm going to describe now an algorithm. Okay? So it's just a description of the steps. The first step is creating an index set. So this one goes from 1 to the number of trials. So in our experiment, this will go from 1 to 50. Okay? And then I also initialize another set that is going to be an index set as well, but I'm going to start it as an empty box. Okay, so I'm going to fill this box later, but now it starts empty, right? So I is full, right, with 50 observations, and capital B is an empty box. Then I take the index set I and I take the maximum number, right? So in fact, in this particular step, M is going to be equal to N. So in the first iteration of the algorithm, right? So 50. Third step, here is where I'm using the revealed preferences, right? So in particular, this notation it means revealed preferences, right? As I mentioned before. And we're going to set E as basically being the set of indexes in the first index set that are labeling all items that are better than this last good XM. So this is X50, the last item in the experiment. I'm taking all the experiments where the bundles peak there are better than the X50, okay? Got it? Okay. And then if the box is empty, then I'm gonna set the value of U of 50 and the lambda of 50 equal to 1, okay? Then in this particular iteration, because this is empty, then I'm gonna go to a step 6, okay? So go to the last step. And now, so say that the 50th observation was in fact, you know, had some items better than it, say X1, X2, right? So now I take the item I, right? And I remove the two observations that are better than 50. So 1 and 2, okay? So now the new index set I has 1 to 50 deleted 1, 2, right? So it's 3 to 50, okay? And now I take the box B and now I fill it with the with basically the deleted objects 1 and 2. Okay? Do you understand? Now with this, I'm going to go back to step 2. Okay? So step 2, set up to m, and now here you can see that this element E is now empty. The box now is not empty, so I have to go to 4. Now in 4, I'm gonna try start setting pretty much the observations to the different numbers using this formula. So I take the mean according to the set E, mean according to the set J, and then I take the minimum of this construction, uj plus lambda j pj, xi minus xj, and the uj. So in general, this is a formula that Varian came up with. So this is in his mind. There is no real reason why they should be. Of course, he's inspired by these first-order conditions and concavity. But this is basically the spark part of the proof. So this is a paper because someone has to come up with it, right? So it's not easy to come up with it just of thin air. So this algorithm basically what it's doing is assigning numbers lambda and um to each point in the data set. So then what I'm gonna do right now is I'm gonna show that the generated numbers using the algorithm satisfy the Afriat inequalities, right? So now let's see what's going on, right? So let's go to step 4 and notice that this is triple mean, right? So first is mean over the index I, then is mean over index J, right? So I'm gonna locate the indexes here, and I'm gonna see this is given the value for U of M, right? So now when I go here, I can notice that U of M has to be less than equal than some particular combination of these indexes. So in particular, I can fix some J index, whatever I want, and then I can fix the index I to also M. So because of the double mean, this value here has to be always below, in fact, any arbitrary pair of indexes, right? So I can choose the index I to be M here, and therefore this thing is gonna satisfy the first inequality. This is the first set of Afriat inequalities. Of course, those are the easy ones to satisfy, but now I have to actually check that the lambda satisfy this opposite inequality that is going to allow me to show the total set of Afriat inequalities. So for lambda, the construction now is triple max, right? So I do the same trick. I have LM here, and now I have to pick these indexes in a way that is convenient. So I just pick for any arbitrary J, the index here, and this Xi here, I replace it by Xm. So this inequality has to hold because this is the max. So it's always above any arbitrary combination of indexes. So I pick conveniently the indexes I want, according to trying to mimic the Afriat inequality. And then by noticing that this quantity has to be strictly positive, I just replace it back. I just basically take this item here in the denominator, multiply by LM, and reorganize terms. And then I have uj minus um, which is this term. This part goes multiplying here. I move sides, and therefore I have LM, PM, xj minus xm. So now I have the inequalities in both directions, right? So mu m less than equal than uj, lambda j, pj, xm minus xj. And then the other direction as well, uj, um less than equal lm, pm, xj, xm. Okay? So this part of the proof, as I told you, is the hardest part, right? So usually it's proven by some deep theorem in combinatorials, but here we're doing a constructive proof. So Afriat, Varian was so smart to do it by coming up with this algorithm that always gives you numbers that satisfy the Afriat inequalities. And the main thing is that if you satisfy GARP, then this procedure will always generate numbers for every point in the data. If you don't satisfy GARP, right, you're not going to generate an output that is complete, right? So the algorithm will stop. So that proves basically that 2 implies 3. Again, this part is harder to interpret. I'm not really I'm not really expecting you to get the intuition from this because there is no really mathematical intuition, right? This step is almost like an integration step, okay? So it's really hard, it's really technical. Now the following step actually is nice. And this one goes from Afriat inequalities to the utility function. So I'm gonna use the inequalities of 3 to construct a function that is concave and strictly monotone and continuous, okay? And on top, that generates the data, okay? So this part is basically an interpolation step. So what I'm telling you is that 3 to 4 basically amounts to the analyst taking the data set and interpolating using a concave utility function, okay? So this is what I'm gonna do now. So again, the proof, this was the key step in the Afriat's proof. So Afriat came up with this construction. So he said, look, I have the Afriat inequalities. Now I'm going to take the minimum over the Afriat inequalities. So why that particular construction? So anyone of you has an intuition why that's the case? So let's try to think about what is going on here, right? So imagine that I am interested on a particular utility, right? So say in particular, the utility of xt, something in data, okay? Then I know, right, by the Afriat terms that this is gonna be below a particular uxt for some other x plus the lambda xs ps xt minus xs, right? So in a way, if I know the utility of any other point in the data, I can overestimate and create an upper bound of the utility of xt, right? So in a way, so if I have something out of sample, I can take the observed utilities plus the Lagrange multipliers and then take the minimum value as an approximation for utility, right? That's the hope. Because of this inequality, I have a series of upper bounds. So I want the closest one. So I'm gonna take the smallest upper bound of the utility possible, right? That's what I'm trying to do. That's the intuition. So here, let's see the construction. So ux is equal to the minimum over the data set, right? Of what? Of the Afriat numbers. ut plus lambda t, pt transpose, x now is a variable, minus xt. So from 3, u, lambda are positive numbers. pt is data and is a strictly positive vector. X is an unknown, right? This is the variable consumption model, and xt is data again. So this is a construction, and I want to show that this utility here is actually what I want. So I want it to be basically continuous, concave, strictly increasing. Okay, and more importantly, I want this utility to generate the data set, in the sense that if I maximize it, it will give me the solutions in the data, okay? It interpolates the data. So the first thing is about continuity. So the functions in the brackets are linear functions. Do you realize that? This is a constant, this is a constant, this is a number, price, this is x, the variable, a vector, and now, so this is a linear function, okay? And now if I take a minimum of continuous functions, linear functions are continuous. So the minimum of continuous functions, you still have a continuous function. Got it? So continuity is preserved under minimum. So check. Concavity. So each function is linear, therefore is concave. So linear is a special case of concavity, right? So now if I take the minimum of a set of concave functions, then the minimum is still concave, okay? So this function is gonna be concave. So this part, I find it interesting to kind of draw it. So let's do that.
So if you took maximum, the function would not have been continuous if you took the max of
No, the max will preserve continuity, but it won't preserve
cavity, right?
cavity. So what I'm doing is this, right? So imagine I have some points here. Okay. And so for each of them, I have a linear approximation. Okay. This, you can think of them as these linear functions inside the brackets. So now, if I take the minimum of them, right? This is a concave function, okay? So this is what's going on. So I have a set of linear functions, and if I take the minimum of them, then this is gonna be a concave function, okay? So in that sense, I'm interpolating. This is a piecewise linear interpolation. Got it? Okay. So, okay. And now the strictly increasing, it follows because lambda t is strictly positive and pt is a strictly positive vector. So this means that this is the minimum of a collection of strictly increasing functions, which happens to be also strictly increasing. Okay? So now this function is what I want. Is continuous, concave, strictly increasing. Now, I constructed a function. Now I have to make sure that it generates the data. Okay, this is the key part. So the first thing I'm going to do is that this interpolation I constructed, in fact, coincides with the Afriat number at the observed consumption bundle. So if I take the interpolation and I evaluate it at the node of interpolation xt, I get as an output the Afriat number ut. Okay. So okay. So assume that uxt is achieved, the minimum is achieved at some index m, and any arbitrary index m. So this is um plus lambda m pn transpose xt minus xm by the Afriat. And then I'm going to assume towards contradiction that this is less than equal than ut, right? So the only thing I have to rule out is that this is strictly less than ut. So imagine that this is in fact strictly less than ut, and this will actually mean that these inequalities, the Afriat inequalities, will fail. So if I have this inequality transformed to an strict inequality, then I have a violation of the Afriat inequality, and then I'm done. So so then this actually has to be that u of xt is equal to u of t. Okay. So the minimum is achieved, in fact, at the point of the Afriat interpolation. Okay, so that was easy. And now using this, I want to show that give me any budget, price PS, and income PS times XS. And now I want to maximize the constructed utility. So I want to show that any X that is in the budget set of PS with this income has less utility, less than equal utility than u of xs. Therefore, making u of xs, sorry, making x super s a maximizer of the constructed utility. So first of all, take PS xs greater than equal than PS x, and then rearranging terms, I notice that this term here is going to be greater than equal than 0. Now go to the Afriat's utility. Because it's a minimum, this is less than equal than the particular index s, right? So this is a minimum, so therefore this will be less than equal than the same inequality part for index s. So us plus lambda s ps, parentheses x minus xs. This part here is the one that I already wrote on the side, right? So this term here is strictly positive, right? It's strictly negative, sorry. XS is here first, XS is here second. So this is the minus of that term, right? So this term here is weakly negative because this is weakly positive. So you basically have u of x, us minus a term, right? So this is reducing the value. So therefore, this thing here is less than equal than U of S. So that means I conclude that the interpolation, in fact, generates the data. Okay? So this proof is very easy, this part here, 3 to 4. And that's actually, you know, the genius of Afriat, Sydney Afriat. So Sydney Afriat actually was a professor in Canada. He taught for a while in University of Ottawa, in University of Ottawa. And then he's Italian, so he moved back to Siena, I think. So he's still active, surprisingly. He's 80 years old. He still goes to seminars. He's very smart. And so he did this paper in, was it 60s or 80s? And then basically everyone ignored him. So Mascolel and the other big guys, you know, they were focused on proving these integrability theorems using partial differential equations and very high level math similar to physics. And they didn't pay attention to this very nice combinatorial proof that actually is way more useful. Because what Afriat did is basically he showed we can test rationality in finite data without obtaining a demand function. So you don't need to do demand function. You don't need to do econometrics in the usual sense. You have a new kind of econometrics. So you can just check this system of linear inequalities to obtain a proof, deterministic proof of whether a data set is rational or not. Okay? And the final step of the proof is the trivial one, which is that the concave strictly increasing function implies a locally non-associated function, right? So obviously strictly increasing is stronger than locally non-associated. So this will mean that 4 implies 1. So now we close the circle. So all of them are equivalent, okay? So that's the proof. Is again, this proof is really a triumph of creativity and is very, very powerful and useful. Now, some things that we have to acknowledge. So not everything is beautiful, right? Is about uniqueness, right? So I'm constructing utilities here, but this is not telling me that I'm constructing a unique utility, right? So this is way beyond the usual metrics. So usually the whole problem in the traditional econometrics world is that you are looking for a unique parameter in some model, right? In order that it explains the data. So this is the identification problem. So usually in point identifying models, you're looking, think of a linear model, right? So you're looking for the slope and the intercept that exactly fits a set of points, right? And so here, you know, you'll never get a unique point. So in fact, the fact that you can construct one utility, the Afriat utility, doesn't mean it's the only utility, right? You can construct an infinite family of utilities. So this is not about identification. So we know this is about testability. So you can test a theory, that a data set coming from a scanner, survey, or experiment is compatible with rationality, right? And you can do it with 0-1 precision. So either it passes or not, okay? And you can do it with finite data, which is amazing, okay? But at the same time, you cannot recover exactly anything, okay? So now we're gonna start thinking what to do with this, because this is a new world, right? So this opened a Pandora box in a way, because, so let's backtrack a bit. So you're now, you're still ignoring Afriat, right? So Angus Deaton, you know, the Nobel Prize, and you don't care about Afriat. You want to do usual econometrics. So you're given a finite data set, right? And you're given 50 points from prices and income. You can fix it to 1. And then you see choices, okay? So what will Angus Deaton do? So he will take and estimate a demand function, right? So any econometrician will try to write a parametric demand function and try to estimate it, okay? Right? So imagine, because we want to live in the world of Afriat's theorem, that this data set, in fact, is rational, right? So, and also for simplicity, assume there is no noise, right? So in fact, you're exactly rational. So you can find, if you had the correct specification of the model, you were able to find the exact parameters that interpolate the data. Now, if you did such thing, so you're lucky enough to be able to hit exactly to the parametric family that interpolates the data, then you will be able to do what? you're able to do, first of all, counterfactual analysis, right? That's the key. That's the key object of interest in any theory, right? Do you agree? So basically, what you want to do is do counterfactual analysis. So you are given an experiment, you're given a survey data, you're given a scanner data. So you want to predict what is going to be the demand and the new price, right? That should be the role of the theory. Isn't that correct? So you want to predict what is the new consumption bundles compatible with a new price out of sample. Do you agree? Yeah, so I mean, econometricians know a little bit what to do. They know what to do with a linear model, with a nonlinear model that is parametric, because you fix the parameters that you train in your data, right? And then you have a new price, and then you apply these parameters to the new price, and then you predict a new consumption bundle, right? Easy peasy. The bad thing about that, obviously, is that if your parametric model is bad, then your prediction is also going to be bad, right? So that's, of course, the issue. Now, the question is, can we use this Afriat theorem to make predictions? What do you think? So who can tell me a sketch of, who has an idea, right, of how to make predictions using the Afriat theorem? And the GARP in particular. So think of the problem, right? So whenever I ask you something hard, you have to rephrase yourself, right? So what I'm being asked is, okay, I have a data set that passes GARP, okay? A data set is a collection of prices and consumption bundles. I'm being asked that I'm giving a price that is not in the original experiment, right? It's a new price, okay? So what I'm being asked? I'm being asked what is the consumption bundle, right, associated with the new price, such that what?
So that GARP doesn't fail?
Perfect. You just did counterfactual prediction in a very non-parametric way. So now I'm going to translate what you did to the traditional econometrician's problem, right? If you have a bundle compatible with a new price, such that the new data set, augmented data set, original data set plus the new point doesn't fail GARP, it means, right, that there is some utility function that basically explains the original data plus the new data, right? So in fact, you're doing counterfactuals that are robust to all the families of utility functions possible. You see? So in fact, you're doing, of course, this is one point possible. What is the new thing, right? So the actual prediction problem is that I have to look for all consumption bundles such that at the new price, GARP is not failing, right? So this is actually a set of predictions. So because we have uncertainty about the true model, which is, you know, a parametric model that we may not find out which is that model because of finiteness of data, I have to make predictions that are robust to model uncertainty. So I don't know the model, right? So I'm going to make a set prediction. The cool thing about this approach is that I don't need to find all possible utilities, right? I just need to actually go and check GARP in this extended data. Got it? Okay, so really, GARP, Afriat's theorem, is a new world of econometrics. So this is super powerful, super robust, and you know, it was just too new and people kind of ignore it. But news for you, they are not being ignored anymore. So a lot of people are working on it, including Nael and myself. And you know, this is super powerful, you know. And so yeah, let's keep going so I can convince you of that. So everyone's clear with the proof of the Afriat theorem? I'm going to take questions. Okay. So I'm going to tell you two things before going forward. The first thing is going to be something I'm going to ask you to read. That is going to be the specialization of the theorem for the strong axiom of real preference. So I'm going to just describe the strong axiom. So this is a strengthening of the GARP that doesn't allow for that actually requires unique maximizers. So remember, our theory only gave us concave utilities, right? But what about strictly concave utilities? If you have a strictly concave utilities, we prove that the maximization must be unique, right? So for functions, so imagine that that there is no possibility of multiple solutions, but you just have one solution, right? We have to then strengthen GARP, and this is a strong axiom. So the real preference relation is acyclic, and so it's not. This is stronger than only weak cycles. This is acyclic. If xt is real preferring directly to xs, then it cannot be that the xs is directly real prefer and weakly real prefer to xs. And of course, t and s are different. So the theorem is basically Afriat's inequalities with some strengthening of the inequalities here. And of course, now we have a strictly concave function. Okay? So I'm not going to prove it because the proof is basically technical in the sense that I have to add a strict concavity by modifying this gap of the Afriat inequality. So it's just a big proof that is just technical in nature. What I want you to remember is that GARP becomes a strong axiom when I'm enforcing that demand correspondences are no longer correspondences, are functions, right? So whenever you have uniqueness in the maximizers, GARP becomes SARP, the strong axiom, okay? SARP is not warp, by the way, right? SARP is still acyclical, right? A warp is just the version with 2 cycles, right? So it's just this local binary consistency, okay? So let's do the forecasting that I mentioned in a second. So Varian, in this famous, well, this paper kind of revived Afriat. So in '82, Varian, he was an MIT student. So he kind of, take out the dust of these papers by Afriat. And he said, look, everyone was ignoring Afriat. Why? So basically, Afriat was ignored because there was no easy computational way of testing these inequalities at the time. And there was not really test, right? And also, we didn't know what to do with it. So Afriat just said, oh, these things are equivalent, but he never told us how to do, for instance, counterfactual analysis. So then Varian, in this econometrica paper in '82, he said, okay, I'm going to fill in the blanks, right? So I'm going to actually solve this problem for you in a way that is actually more manageable. So the first thing he do is actually define counterfactual analysis. And this is the problem I told you. So the variance supporting set is that I'm going to be able to predict consumption bundles at a new price and income level. And the way I'm going to do it is very easy. I'm going to take all the X consumption bundles such that the union of the original data set. So I'm going to correct the typography here. Union the new point pk with a candidate bundle such that pk plus 1 times the bundle is equal to the new data point, okay? So this is just enforcing 2 things. First, it's enforcing that the extended data set with a new point satisfies GARP, plus that the new bundle multiplied by the new prices is equal to the new income, okay? So this object is a set, so it might not be unique. In general, it's not unique. So it gives you a set of predictions, okay? A set of predictions. And it turns out actually that you can check it very easily, right? So you can actually take, you can verify that X belongs to the set if 2 things hold. First, it cannot be the case that at the new prices, the new bundle is really preferred to any observation there whenever xt is strictly real preferred to x, right? And of course, we can do this with inequality, by the way. With equality doesn't matter, so just that. And of course, the inequality here, or the equality here of the budget hitting, so hitting the budget line. So that's it. So it turns out that doing this counterfactual problem is super easy. You go to a computer, you write down this program, which is a linear program, and you're able to find all consumption bundles compatible with the new price. And you don't need to do a model, a parametric model. You don't need to do machine learning. You don't need to do anything. And in fact, your prediction is robust to it doesn't have any more misspecification bias, right? It's perfect. Okay. So then you will say, then why people are not doing that, right? So, because I'm sure most of you have never heard about this before, or have you? Maybe you study variant, the baby variant paper, the baby variant book. So who has heard about this forecasting with reveal preferences before? Nobody? Well, it's common, right? So most of us just learn the traditional econometrics, right? So we fix some sort of parametric model, we recover the deep parameter, and then we use the deep parameter to predict out of sample, right? But there are a lot of issues, right? So a parameter basically means that you are choosing a particular point in a set of models that explains the data. So how do you handle, a collection of models, and how do you make predictions in these very complex models where you don't know the correct specification? So Afriat is telling us, look, you can actually just use the content of the theory, the fully non-parametric content of the theory, using reveal preferences. And we know that all rationality can be translated to GARP, which is this consistency condition. So now, given that I have all the non-parametric content of the theory, I can use it to do non-parametric counterfactual predictions, right? Which is amazing. So this is way better than all these machine learning predictions and so on, because these predictions happens to be global, right? So so anyone is familiar with, predictions with, highly flexible models? Who has done some sort of metrics or some sort of analysis using, kind of machine learning tools? Anyone here has some experience with that? No? So a little bit the problem is, let's say you want to predict this demand problem, right? And you say, look, the issue is that I have to find the true model, right? And then you start pretty much fitting these points, you interpolate them. And, even you use a very flexible thing. The issue is that out of sample, there are many ways you can extend this model, right? So the only way usually predictions are done in machine learning is by using continuity. So you can only handle prices that are very close to the sample. Because if they are too far, then you really don't know how to discipline this model, right? It can go anywhere, okay? So that's why this is this model is actually robust. Okay, yeah, for instance, ensemble models. In particular, when you're trying to predict stuff, right? So you can have two kinds of models, very flexible models of machine learning where it's almost theory-free. And in those cases, it's very difficult to extend out of sample in a very global prediction, because the farther you go away from the in-sample training, then the model can really take any particular direction. So I'm going to do a graphical explanation of that. Okay, so I'm going to tell you the following problem. So this is a problem of the law of demand. So it's a special case of rationality. So say I have 2 points, right? And basically this is quantities, and you have prices here. Okay. So what is the reveal preference analysis, right? I'm asking whether these two consumption bundles and quantities and prices satisfy the law of demand. And the answer is yes, right? So the higher the price, the lower the quantity, right? So therefore, these 2 points satisfy the law of demand. So therefore, this is rational, okay? In a stronger way. Now, say I want to fit a model, a fully non-parametric model using some machine learning technique. So then what do I do? So for instance, I can pass a point like this, and maybe I can pass another like this. Maybe I can do yet another like this, right? And so on, okay? And maybe even another one that goes like this. So look at this area here. So this is the sample, right? And all these curves here are really close in this area, right? In this circle. So all of them, the predictions, say I have a new price here out of sample. What are going to be the predictions? Well, according to the model you pick, the closest you are to the data, you're gonna get very close predictions, right? But the moment you start moving this PT+1 to very far away from the data, then what happens with the prediction? Really everything goes, right? So this would be a kind of a model-free training, and then the issue with prediction out of sample, right? Everyone understands that point? So my point being is that only locally you can make predictions using that, using continuity, okay? Yeah, so one thing that is very successful now is that you use this kind of nowcasting. So for instance, in macro, instead of trying to predict the following year of GDP, you try to predict the following month or the following day even, right? Of expectations, for instance, right?
So is it kind of like you just restrict your neighborhood's size, so to speak, on okay.
Now let's think of this other problem instead. So you still have the 2 points, right? But now you have a theory in the sense of revealed preferences. So you know the law of demand holds, okay? So now you don't need a model anymore. You're still given a new price, right? So this is price 2, this is price 1. And now I have here price T+1. So this is the out of sample price. So, now I have a consistency condition, right? Now, my restriction is that the law of demand has to hold in the extended data, okay? So then using that condition, what is my prediction? So what is my prediction using the law of demand, only the law of demand? Who has an idea? So basically, I draw a line here, right? And it has to be downward sloping, right? Any point here is a prediction, right? So of course, this is the intersection of this segment of the price with this area. So my prediction is this segment here, okay? So of course, this is not everything goes before. Because now I have a consistency condition out of samples. So I know that whatever happens out of samples, it has to be downward sloping, right? Weakly downward sloping. So it can be flat as well here. Now, so this is lame if you want for 2 points, right? You see? So 2 points is kind of lame because this predicted set is too large, okay? You see? So now these methods really work, the non-parametric methods I'm presenting you, whenever you have a lot of points, right? So right now, instead of having 2 points, now say I have, for instance, 3, 4, and so on, many points. So now, the points I have, I'm being able to now refine the prediction, because now only this area is going to hold, right? And of course, this is 2-dimensional as well. The purples are really important when the low is one, right? Because we're low property. But in real life, we have also dimensional theories and backwards in multiple dimensions. So the more data points on budgets you have, the more precise the predictions are going to become. Okay. And what is surprising is actually in the example of the experiment that I told you with 50 observations, you can actually get very, very precise predictions out of sample. Okay. So usually you need these individual data sets of 50 or more. So in other words, if you have a scanner data set with weekly trips to the supermarket, going to Costco, and you have a year's worth of this data, so that means you have actually 52 observations or so, right? So a lot of observations. Then, this is data that you can use to predict in a nice way, okay? So this is a new way to predict. And what I'm saying is that it doesn't matter that the prediction is far or close, because it's about consistency conditions that are global, okay? And the more observations you have, the better these predictions become. And that's why a little bit why we didn't use them before, but now we are interested in them. Because these variant predictions work well with large data sets, right? And also now that we have better computers, okay?
Sorry, so I have a question about this example. So let's say you take millions of data, and that kind of aligns with the demand function, so the downward sloping. And let's say you find out of a million, like 1 or 2, like a very small number of them kind of goes outside, which would break the warp. But you observe millions, so you would think that it's just an outlier. So would you just reject it take out the data and just
Yeah.
assume it still fills a gap, or
You,
just
you,
say, oh, this
you
is
find,
warp?
basically what Tyson is saying, let me rephrase it, right, is that imagine you have 1,000,000 points, right, and then some point here, you know, at some point in this experiment, this agent got distracted, right? His cell phone was, you know, notifying that he has a message, right? A new problem set from micro. So he gets distracted, and then, you know, this point is breaking log demand, the blue point, okay? But Tyson is saying something else, right? He's saying, look, you actually have a lot of points, right? And then only one of the 50 points is breaking log demand. So what do I do with this data? So according to the Afriat theorem adapted for this simple example, so your finite data, still is finite, even if large, will fail log demand, right? And then you're done, right? You cannot do predictions. So Tyson detected the Achilles heel, basically, of this problem, right? So if you have mistakes, then what do we do, right? So of course, remember that this is the same problem econometricians already face, right? So let's remember that econometricians started with the interpolation problem, right? So you have 2 points and I want to fit linear lines, okay? But what if I have some point out of there? So what do I do with that? Okay, then they invented OLS, right? Okay, so they say let's minimize the distance, for instance, right? So some notion of mistakes, okay? So what is the notion of mistake here? Okay, welcome to the research agenda of Roy Allen, Victor, Nair. And so that's what we're doing basically. And that, a lot of people are working right now on that. And that's the question, right? So if you're able to have a good way to deal with mistakes, then you have a full theory that can actually deal with data, right? So that's what I'm going to tell you a little bit today, okay? Yeah, but this is very exciting stuff because you're asking the correct question. So right now I have a new animal, right? Which is set predictions, consistencies on points. But I still may have noise, right? Mistakes, many things that add issues to the data. So what do I do if one point fails, for instance? Should I throw the data or do I remove that point, for instance, right? So that's one way, right? If there is only a few points that are breaking the data, I just drop it. But I need something more systematic, right? So that's what I'm gonna show you now, okay? So before going to that part, the one motivated by Tyson's question, I want to give you a quick overview of welfare, okay? So the other reasons you may want to do estimation of parametric models is that in the end, using the parameters, you may want to get a parametric utility, right? And using a parametric utility, you can do welfare analysis. Okay, but that's the cool thing about reveal preference approach, Afriat approach, is that maybe you can actually just compute bounds on welfare using the Afriat theorem again, right? So what I'm going to do is define a monometric utility function, which uses the expenditure function. And what it does is basically tells you in monetary terms the utility. Now, the utility usually is measuring some weird units that are utils in the mind of each consumer. So I want to transform these units into money units, okay? How do I do that? Generically, remember the expenditure function, right? So the expenditure function for a fixed price, it transforms utils into money, you see? That's basically the nature of an expenditure function, right? So I take the utility part of that expenditure, I input there the utility of X, and I get myself a new utility that is price dependent, right? Represents the preferences, the same preferences, because it's a monotone transformation. So for a fixed price, it's a monotone transformation of the U of X. So if you go back to the properties of the expenditure function, you will find out that this is monotone on the U, okay? So this is in fact a utility, is still a utility, well-defined utility of the same preferences. The only difference is that this M P of X, the money metric utility, is measuring money. So in dollars of this price. So for instance, if you use for that price, the CPI of 2019, then this is going to be in dollars of 2019. Okay, so that's the money metric thing. So now, right, I say I want to estimate this. Okay, so say I want to estimate the upper bound of the money metric of a given price, right? So what I'm doing here is saying I'm gonna give you a new budget, and I want to know what is the upper change in your welfare. Okay. So how do I do that? Well, this n plus is going to be the minimum of the multiplication of price times xt. So let me look here. Transpose. Okay. This is the inner product, so I don't want right now to damage the notation. Subject to what? To xt, the data being reveal preferred to x. Okay. This is the x here. So basically, you start with a data set that satisfies GARP, and then you solve this problem, and this will give you the maximal possible change of welfare if you were to consume X given this price level. So basically, you are solving kind of an expenditure function because you are minimizing the expenditure, right, given data constraints. So instead of minimizing in terms of X being flexible, you are minimizing over all X's that are in the upper contour set of X, right? So the constraint is telling you all XTs that are reveal preferred to X, so are above, are in the upper contour set of the item of interest X. So this is a formula. I'm not going to show it. It's beyond the scope of the class. But the interesting thing is that this gives you, of course, an upper bound of the welfare. So I also can do a lower bound. And how can I do it? Instead of using the upper contour set, I can use the lower contour set, right? So I'm not going to write it right now. And together, they provide bounds on welfare. So now I can tell you for a new consumption bundle, what is going to be the maximum amount of welfare money metric that you experience versus the lowest amount. And using that, I can bound the compensated variation, equivalent variation, okay? So actually, Varian applied this to an electricity plants construction paper. So yeah, so this is actually very useful and very clean. So you will be doing your welfare analysis without doing partial differential equations, without doing crazy stuff. This will be a very nice linear program, right? So again, Afriat is very powerful. But again, all of this sounds too good to be true, right? And the issue is basically what we discussed a moment ago. Basically is that Afriat doesn't allow for mistakes in the theory, right? And most theories, because the data we have in social science is imperfect, they need noise. So let's make a stop here. So who studied, classical physics in high school, right? So you remember these parabolic theories of, these are deterministic theories, right? So you have an initial speed, have an acceleration, then you launch a projectile, and you can compute exactly the trajectory, the parabolic trajectory, and you know exactly where it hits the ground as well, and the angle and everything else, right? This is a very precise theory that is fully deterministic. That's the key, right? Now, if you have a perfect laboratory, we're having the vacuum conditions, you can actually exactly predict where this is going to land, right? And you can exactly test this theory. Now, let's say you don't have a perfect laboratory, so you have to do it in your backyard, in the backyard of the university. What do? So you throw your projectile, and then there's going to be wind, there's going to be rain, and then eventually, your prediction is going to be way off. So what do? You reject the Newtonian physics at that scale, right? That's a little bit our situation. You see, guys, that's the situation we're in. So nobody has designed a vacuum experiment. So we kind of have this noisy data. So just for a second, remember the description I told you about the survey data, right? Very crappy data, right? Let's be frank. It's very crappy, right? You don't have real prices. You have CPIs which are constructed with a lot of assumptions. They are composite goods constructed in terms of estimated weights on the basket of goods a typical consumer purchases in Spain. So there is a lot of pre-processing, right? So some statistician, very smart, of course, try to do his or her best, But in the end up with some set of arbitrary rules to construct the CPI. Let's be frank, it's not raw data, right? It's very pre-processed, very, not nice data. And then, you measure consumption, and consumption is done by recall. So basically the subjects of interviewing a survey, they're given these diaries, and you voluntarily have to go and write down everything you purchased and consume the last quarter. And some people are very orderly, they're gonna do it the day they purchase, but a lot of them are gonna try to do it before the surveyor comes, right? And so what do you think is gonna happen with that data?
There's just going to be like a lot of holes, or just it's not going to follow like a behavior pattern that you might expect.
Sub-reporting is an issue, and reporting, not reporting, but also measurement error, mainly measurement error, right? So people are not going to report correctly. So in the end, okay, even say, okay, that data that is super granular is crappy, I don't care. So because it's too difficult for me to ensure that I actually report the actual consumption value. So let's not even focus on that. Let's focus on something simpler. So if I ask you, what is the fraction of your, so first of all, I ask you, what is the total expenses in the last quarter? So maybe you can estimate it, right? So you say, okay, monthly, more or less, I spend this amount. So I spend total $1,000 in all my expenditures, okay? Now, from the $1,000, what fraction do you spend on food? Who knows your fraction spent on food? On rent, on transportation. So you can estimate, right? So more or less, but here, that data is a little bit better. So surveys are good for that, right? So you estimate the fraction of expenses of the total expenditure you do in certain categories, okay? But the issue is that you may forget what you did that month. You may actually be what is called social desirability. For instance, imagine that you're a smoker, right? So you spend a lot on tobacco, right? And then, of course, that's all age. So you do, e-cigarette, right? But you spend a lot on that. And then, are you gonna tell that to the interviewer, or are you gonna tell them that you're actually spending a lot on food, right? So people, because of social desirability, may lie. They may over-report, food, and then under-report these other things. So also it's difficult to estimate things that you do very often, like food may be well estimated, but maybe you don't remember exactly how much you spend on transportation, because if you don't have a clear commuting pattern, and maybe you're going also for entertainment, for transportation, for purposes of entertainment, you're gonna get confused, right? So in some, you're gonna make mistakes. So everyone makes mistakes, and you're gonna end up misreporting, under-reporting expenditures. So I'm not even gonna deal with not reporting consumption, because I'm just gonna ask you this level of question, allocation across categories of goods, which is easier, okay? But even so, you're gonna have measurement error, okay? So I have a paper with Nail that just got accepted into the Review of Economic Studies, one of these top 5 papers. We're very proud of that paper. We worked a lot, many years, since I started as a professor 5 years ago. And in that paper, we have a huge chapter, subsection, on measurement error on all these data sets and the sources of it. So we document why in surveys, for instance, you may have measurement error. And the main source of measurement error in surveys is, as I mentioned, consumption, right? Because this is what people are trying to recall, and is very badly reported. Turns out that expenditures and the fraction of expenditure you actually you are given to the interviewer as fraction of expenditure on food, on transportation, on recreation, and so on clothing, those are a little bit better. But the only thing I can be sure is that if I take all the Spanish people in a time period and I average their reported expenditures, right? And then I get access to a validation data where I actually know factually the expenditures that they did, and I compare the shares on those expenditures with the reported data, the average will coincide. The average will be good, okay? So that's for surveys. And in general, we're gonna see that sometimes, average data, so the data that macro people use, is of course better quality, just because noise gets canceled out, okay? So that's important to remember. Right now, we're gonna go back to this experiment that I mentioned. And I told you already the results of the previous class. So we have 50 observations, and then we have that only less than 20% of individuals pass. So this is the question by Tyson. So, and what do we do? So do we throw away the data of the 80 guys? So I'm gonna give you two solutions. None of them are final. The first one is called the Afriat index, efficiency index. So I'm gonna describe it very quickly. This I want to spend a little more time next class, so I'm gonna stop there. I'm gonna go there later. But now I'm gonna give you a quick overview of what we do with Nail. And so just that you have perspective of what is missing in this Afriat theorem, that is what we're trying to fill in the blanks, right? Is that we basically use an experiment very similar to the one I presented, that instead of having 2 goods, now have 3 goods. So here agents are presented with a projection of this 3-dimensional budget, right? So you see this 3D graph in the computer, and you have to pick from the surface, right? So in 2 dimensions, a budget line is just a line, right? But in 3 dimensions, what is a budget? Is a 3-dimensional object, right? It's a polytope. So then, what is the budget line? Budget line is actually a phase of this polytope, right? So you have to pick there. So they actually did that. They created a 3D graph representation with 3 axes, and then you have to pick there. So 3 goods. Of course, it's harder to understand prices. You're gonna agree with me. And they have to maximize that. Okay, so when they did this for 50 trials per individual and 154 individuals, again, students in NYU and Berkeley, then the passing rate was even lower than the 2 goods case. Now it's only 12%, okay? So out of the 154, only 12%, almost 10%, passed GARP. The rest didn't. Now the question is why, right? And that's what we explore with Nail, but also is related to the question by Tyson. So maybe it's because the data we're getting is noisy, right? It's bad data in the sense that we don't have a vacuum. What is the main issue in this experiment? Well, the main issue in this experiment is that people may do 2 kinds of mistakes that are not reflecting their intentions, but are actually frictions of the experiment. The first one is that instead of observing your consumption, we will observe true consumption with a star plus what is called Kremlingham. So I'm choosing with my mouse on this budget line, right? And then what happens if I'm not able to actually do it correctly, right? So I'm making a small mistake, and then actually I point to a different bundle. Remember, a choice is a point. What if I'm not able to exactly get to the point I wanted, right? So this first error is called Kremlingham, right? So this is just an implementation error. And the second potential error that you have is misperception error. So you try to estimate prices by looking at the budget line, but this is a graphical representation, a very complex one in 3 dimensions, right? Now from this, you have to infer the P1 over P2, P2 over P3, so the relative prices to solve your first order conditions, right, if you're doing that. Then we argue that the price that consumers use to maximize is in fact the true price plus misperception, okay? So this error here is called misperception of prices.
And misperception could be plus or minus, like a positive number or a negative number?
Yeah, in fact, this is a vector perturbation, right? So it can go in many directions. So yeah, so instead of thinking that price is 1 over 2, you think is 1.5 over 2.3, right? So it can, and then the other right ratio prices may also be affected. So this structure is very general. It allows a vector perturbation, okay? So GARP has to hold only for the true data, not necessarily for the mismeasured data, obviously. So what do we do? So what we do is basically create a methodology that allows you to use knowledge about the errors. So we use validation data from an experiment where they actually check these errors in using the mouse and in how you perceive the points in the graphical representation. And from this data, we conclude that Kremlingham errors are actually centered around 0, as well as misperception errors. So what it means, and this is usually true in many experiments, right, is that even if you have the void, if you take all these 154 individuals, some agents will misperceive a little bit like this the price, others like this, right? So in the end, you have 154 of them. If you take the average of them, then you're gonna get the correct price. The same with the Tremblingham error. Some people are gonna be above, some people below, left, right. If you take the average across them, you're gonna be in the correct point, okay? So we actually have validation data for that. People do that. And then using that, our methodology combines it and tests the null hypothesis that every individual in this experiment, the 154, are consistent with GARP in the true data, P star, X star, right? Conditional to the measurement error, these perturbations here that make the data less powerful, right? They make it easier to pass. So in the extreme, if I don't know anything about measurement error, then everything goes. So I can always find a set of perturbations that will make the clean data pass GARP, right? Do you understand? So I need to have information about measurement error. So we get it from this validation data. So now knowing something about measurement error, I can now average out this thing. So basically what we create is kind of a version of GARP allowing for measurement error. And then using that, we are unable to reject rationality, okay? With pointing out to the importance of misperception of prices. So with that, I'm done. So this is the end of the class. I'm gonna be here for, again, 30 minutes or so and taking questions. So go ahead. You're also free to go if you don't have any questions.
Hello, Victor. I have a question. So I was wondering, like, how did you have access to the real data?
Yeah, so in this particular experiment, what happened is that a professor in Toronto, Matthew Webb, with other researchers in Israel, they ran an experiment where they not only collected the data on budgets and points, but also collected data on the movement of the mouse. And also they collected data on motor tasks. So they asked them to point to a particular coordinate in the budget, and then they measure the distance from the coordinate that is your target and the actual point in the mouse. So with that, we actually have a task to elicit in the same experimental interface, then the motor error. So that would be the Tremblingham error. So when we went to the data, to the original data, this is publishing in Nature, in our Journal of Nature Communications. So the data is available for everyone for replication. We took it and we checked and verified for each individual that this condition hold. So the motor errors of the mouse average out, okay? So we did a hypothesis test and this passes. The same for misperception. So for the misperception case, instead of telling them a graphical target, they gave them coordinates as numbers. So say you want to go to this particular price. So locate it with your mouse. So then they saw how people map numbers to points. So the graphical from the number representation. So using this, we got this misperception error. And then we can actually now find, we also verify that this condition hold. Now, the important thing about our methodology is that even if we are motivated by external data, which is this augmented experiment that these guys in Toronto and Israel run, we can actually test jointly the null hypothesis of GARP and jointly with the assumption that this Tremblingham error and the misperception error are centered around 0. So it's a joint test. Now, we use the validation data to say, look, given that in the validation data, this thing happens to be true, then, you know, the fact, if we were to reject GARP, then it would be actually the fault of GARP, right? But in this particular case, we are not rejecting GARP. So GARP passes for the case of misperception. If we allow for Tremblingham alone without misperception, then GARP is failing. So that means that, you know, GARP, of course, is passing, but Tremblingham is not enough to rationalize the data. So again, this is remember, so we want to go back to the idea of OLS kind of thing, but for these set models. So how do we think about error in these models? And this is the way to do it. So we are thinking about consumption and prices to be measured with error, and then we allow error to be known only at a certain level, like for instance, average information. And then the methodology we provide is being able to combine average information of measurement error with GARP to be able to test this statistically.
Okay, thank you.
I'm just curious, for these, so clicking mouse, the trembling hat, I think you call it, enemy perception, wouldn't it possible that you increase this as the number of experience goes up for each individual because they kind of get tired? You know,
Yeah.
First question you focus on, then up at the end of 50, people probably, you know, focus less. So it wouldn't be identically distributed. That's what it feels like.
Yeah, so we're not assuming this IID. So we're just assuming it's independently distributed, but it's not identically distributed. Oh. So Varian has a paper that he assumes is normal and identically distributed. So yeah, these things may not be normal. But so to answer, the only thing we're assuming is independently distributed. So each guy here is in a computer, right, isolated from the others. So independence is not an issue, right? Then yeah, but we don't assume identically distributed. What you say, however, is true, in the sense that, for instance, it may be that, for instance, the variance is changing, right? So in the later periods, you have more mistakes, but we don't rely on that. But that means, for instance, you cannot improve predictions using this kind of approach by using variance moments, right? Because maybe variance is too volatile.
Right.
Yeah, but yeah, so what I know from checking these experiments with detail, people do get tired. So like in the newer experiments, they only do 20 trials instead of 50, because apparently after 20, people start kind of going crazy. Makes sense. So our methodology is kind of robust to that, but it means that the information you're getting from the later periods not really helping much. So like in the new experiments, they just elicit 20. Yeah, but that's more like the art of experiment, right? Our methodology is robust to that because we don't rely on the
so you don't assume that basically, and you just incorporate that it may not be true or it could be true, so you just
so we only use the first moment instead of variance. Okay. We don't rely on variance.
Quite very interesting. Thank you.
Good, I see.
Since this stuff is all like pretty new, I'm guessing it's not in like any textbook that's out there.
No, so that's why the notes are the main resource, right? So of course I can post the link to our paper. Again, as you notice, this section is very short and not technical. So this one, of course, the purpose of it is that I'm not going to test you on this, right? This is just presenting state-of-the-art evidence on applying the Afriat term. So whenever it's something I can test you on, I'm going to provide details. So summary, yes, this only lives on the notes and on papers because it's new. So if there's interest, I can give you the link of my paper. You can also find it online, of course. And the second part of that, as more a clarificatory notification, is that I'm not going to test on these things that are not formal. Example, variant supporting said yes, but this measurement error stuff, you're not going to do anything about that because that's usually second year stuff. Okay.
Hi, Victor.
Yes.
I have a question about how you deal with measurement error. I think if we can solve it like this way, since these measurement error are randomly and low systematic, so we can randomly choose the samples to do some regression, and we repeat this regression again and again to get a bundle or many regression results and combine them together to solve this problem. Can we just do in this way?
Yeah, so that's an interesting idea. So you're saying kind of, if I understand correctly, So what you want to do is some sort of permutation test. So I didn't get completely. So you want to do, so you understand that the error is not systematic, right? And random, right?
Yeah.
Yeah, so basically what we're doing is Afriat, if you notice, is only using the time series information, right? So the individual data. So when you have noise, you have to use the fact that this is independently distributed, right? And so,
Yeah.
so now we use the panel data set instead of the time series. So we pull together all the subjects in this data set of the 154. And now Afriat holds in the time series dimension, right, for each of them, for the true data. But cross-sectionally, we are averaging out the non-systematic error. So in that way, we actually add another dimension to Afriat because Afriat only works time dimension, right, in the vertical way if you want. And now we add.
Maybe we do not need to use panel data, just use your, so you have a data set, a sample of data. I think you can run, maybe there are, for example, there are 100 points. You first choose 50 points randomly, and then again choose 50 points randomly.
Yeah, it's a good idea actually. So there is a recent paper doing that. So what they do, so the things that you can test with that are more limited, but you can do this. So you can say, imagine now that you want to ask the question whether the rationality guard does a better job explaining the data than just a random choice. So imagine you choose just randomly from the budget line with uniform distribution, right?
Yeah.
So you can, using what you say, you can test whether rationality, so the null being random choice versus the alternate being rationality. So if you reject the null, then rationality is better than random choice. So they do exactly what you described. So they take the data set and then they start permuting it, right? So taking random samples of it. And then in each of them, they test pretty much GARP. And then they see the fraction of times this passes and they create a test. But this only tells you conditions under which rationality GARP is better than random choice. So random choice is kind of, is the worst for prediction because out of sample, everything goes uniformly, right? So it's completely uninformative. So you are basically asking, is the rational model more informative than random choice, right? So yeah, so I agree. So one of the challenges of this literature is kind of the direction you're proposing. So can you use just the individual data with some maybe more assumptions on the Tremblay-Hahn error, the misperception error, to do something at the individual level, right? And then if you do that, if you come up with a new test that allows for error in the individual data, you can actually make individual predictions. But I'm sure that you need more assumptions than we do, because given that you have less data, you don't have the panel anymore, then you have to assume more or have to know more about measurement error, okay? Because that's kind of the trade-off. Less data, more assumptions, right?
Yeah.
So that's the way it goes.
Okay. Oh, I think I make a small mistake. If we combine the different regression together, it's just like a panel. But if we separately treat this data and analyze this relationship, we don't have enough samples, data samples.
Yes. So I agree. That's a very interesting idea. So yeah, I think that's actually what people are. This is an open question, basically. So ideas on that sense are very welcome and new because a few people know what to do there, right? So this is, as you see, very new.